And as usual, we should have a theme song. There you go. Okay. So, well, good afternoon, ladies and gentlemen. Welcome back to Mathematical Method for Physics. Now, um, it's recommended that I should have a theme song to give the audience a sense of new beginnings. I don't know. Maybe I can make my own theme songs. I've been practicing along with making a lecture. I've been practicing this music, which I heard from TV show. It's very nice. It goes like this. พี่เอารักมาฝากเป็นความรักจากชายคนหนึ่งฝากถึงสาววัยขอฝากหัวใจเอาไว้ในห้องหอหัวใจของห้องที่เขาบูชาพี่เอารักมาส่งจากชายซื่อตรงคงคำมันไม่พันวาจารักกว่าพื้นดินและฟ้า Oh, something like this. I need to practice some more. Thank you very much. Let me give myself an applause. Okay. All right. So let's get back to business, people. What I left off from last week was this particular slide right here. Okay. So I said that we were going to continue with the metrics for this case study of optimization, and then begin the next lecture of numeric PDE, partial differential equation, and ODE. Okay, so let's begin this optimization. Now, when we talk about optimization, it actually is related to the previous topic that we studied before, and that was root finding. So let me, in the beginning, before going into optimization, let me review root finding. Oh, I have this, let's see, messages. What was that? Okay, what did, I've lost the chat. It should be in the team somehow. Let me I can't see your presentation. Oh, of course you cannot see my presentation. Thank you very much. I almost forgot. I forgot to share. Thank you. The screen. So damn it. Let me go back a little bit. What should I do? I should share the screen, the window. Very good. Thank you, Dewey. Almost have a total failure of lecture. Okay. So let me, where was I? I was here, optimization, okay, the first slide. Here, the topic of optimization is related to root finding. So let me first review the root finding that we have studied in the previous lecture. In here, you will see that if we have just a simple equation, that fx equal to 0, and you want to find the x value that satisfies this equation. We call that the root of this fx. So what we did previously with the Newton method, in the beginning, we began with the initial guess, x0. Anything that you think is a good idea for this solution. And then we proceed to the updating scheme using this very nice Newton method updating formula, and we keep going into cycle, you know, to x0, x1, x2, x3 until convergence is met, or until fixed point is found. Now, suppose we want to go to somewhat more complicated situations. That is, we have more than just one variable. We have like 3 for this example, or 5 or 6, or any number of variable that we want to solve. And then, of course, we're going to have the number of equation. In this case, we have 3 equations and 3 unknowns. So how do we find the roots or the solution of this system of equations? Okay. We begin with the same concept, okay? But now, instead of having just one variable, like in the previous case, only x, now we think of this unknown as being a vector. So you have a bunch of values, x, y, and z. So we group them into a nice vector, and we use this arrow on top to signify that it is a vector. So begin with initial guess R0. And then we're going to use the updating formula for a system of equations. Now, it is still based on Newton method, but the formula is changed just a little bit. So let's look at this structure, the pattern of these 2 formula. We have this previous iteration Rn, but in vector form. Now we have xn, very similar. And on the left-hand side, we have x for the next iteration, xn plus 1, and that is R vector for the n plus 1. Okay. So, and also the updating term here, we have minus sign there and minus sign here. The f function, the f vector. Now why do we have this f vector over here? Well, because now we have many value of the f. So we have f1, f2, f3, and therefore we think of this f together as a single column vector, like so. Now, if you focus on this blue symbol over here, for one variable, we have 1 divided by f prime. Okay, that's for one variable. For many variables, we have the inverse of this J matrix instead. Okay, so they're very similar, but now we are talking about matrix and vector multiplication. Now, still the same concept, which we'll see later on in the actual example to make it clearer. But for now, you should make a mental note that we are turning this 1 over f prime into an inverse. So 1 over becomes an inverse of this nice matrix J, okay, which we call it Jacobian matrix. Okay, we'll see in the next slide how we compute a J. But at least here in the beginning, you see the structure of the updating schemes, very similar for many variable system. Okay, now let's get to an example for you to see exactly what happens in this system of equation. Suppose, in this case, I have 3 unknown, x, y, and z, and I have 3 equations written in this form. Okay, now on the right-hand side, I have this info box to show you the steps, but let's focus here on the left panel of the slide. So we have these beginning equations, 3 of them, and 3 unknown to solve for. So what do we do in the next step? We need to convert this into a standard form, meaning that on the right hand side need to be 0. Okay, so how do we do that? We simply just move or this 4 to the left hand side and become minus there. Now the middle equation is 0 already, but the third equation here we need to change this to x minus y. Okay, so that's a very simple step, just to warm up the process. Okay, now remember for the updating scheme, we need to know the vector of the f. Okay, the values of the f function for f1, f2, f3. So we define it here. Now once we know the left hand side, we then define the value of the f vector like so, this way, that way, and in the middle. Very simple, very simple. Now in general, this f is not going to be 0 unless we are exactly at the perfect solution. But in general, it's going to be some number which is not 0, okay, unless we add the solution. So once we have defined the f vector, we don't proceed to the J matrix. So what is it? J matrix is a Jacobian matrix. It is a first derivative matrix. Very similar. Let me go back to the previous slide for the one variable case. Very similar to a single x. Here we have f prime, okay, first derivative value. Now it becomes J, the first derivative matrix. So how we do this? We just take the f function, which we have it already here, and then take the derivative respect to the x, the y, and the z, according to this formula here. So it's very simple. It takes a very simple math skill that you do here. So let's do that together, one by one, just to warm up the beginning of the lecture with a very simple exercise here. The upper left corner, we have df1 dx. So what is f1? Well, that's the expression for the f1 value. You take the derivative, you move number 2 down here, become 2x for the first element. The next element will become 2y. To take derivative respect to the y value, you get 2y. Forget about this x here because we are talking about the y derivative at this point. For the z, you get 2z. Okay. Now what about the next row? The next row is going to be the same concept, but with the f2, f2, and f2. Of course, it is 0 here because there's no x value in the second row. So we have no dependent on the x. What about the y? Still 0. And the z is 1. And we go quickly for the third row. You get something like this. Okay. So we have all the ingredients ready to proceed to find a solution of this nice equation, what they are. Oh, I suppose I have this blocking the view of here. Okay. Now, to actually proceed to the iteration, we don't really need the J Jacobian. What we need is the inverse of Jacobian. Now, it's going to be much more difficult to compute the inverse. So I usually use free software. In this case, I just plug in this matrix and then look at the answer from this Wolfram alpha. You can do it by hand, or you can use software packages to solve for the inverse numerically. Okay, so now let's go easy with that here and then just copy the answer from Wolfram because you want to see the process in the beginning. Okay, so I plug this J matrix into Wolfram and I get this inverse like so over here. So let's proceed to the iteration. Okay, well, now we have all the ingredients. Let's pick an initial guess, R0. Remember, we have 3 unknowns, x, y, and z, and we group them into a nice vector. Let's pick a simple one, 1, 1, 1. So what do? Once we know the initial guess vector 1, 1, 1, we simply then compute the f. What do? Here's my f. If I say 1 plus 1 and plus 1, that's 3, minus 4 is minus 1 at the end. What about the middle? The z, or is 1. What about the last row here? It's 1 minus 1 is 0. So we have the f value for this iteration. Then we compute the inverse of the j and use that formula here. You plug the number of x, y, and z at this location, and you get back the j. Okay. Of course, now the inverse of the j matrix. Sometimes you have a constant which does not change through the iteration. But sometimes you have this formula which depends on x, y, and z. Okay, so we do this substitution. You get 1/4. For example, you have this here, 1 divided by 2x plus 2y. But since x is 1 and y is 1, and therefore we have 1 divided by 4 in this case. So you go quickly through this process, which I'll go quickly. Now we used this Newton's updating scheme to compute the R1. So I do that here. I got 7/4 and 7/4 and 0. Now it's going to be difficult to do this by hand. So I have prepared a Python code for you. Let's go look at that together. See the programming. Okay. Now let's change the thing to to our class website. You go to there and then you click on the optimization here, number 6. Click on that, which I have prepared the Python code for you for this optimization. Now let's wait a little bit and see. Oh, okay, very nice. Let me zoom in a little bit so you can see it better on the screen over here. Now in this optimization Google Colab notebook, I actually have 3 sections for you: the root finding and an optimization, and then the Quasi-Newton optimization. Let's look at the first section of this here. Okay. Now we have some explaining text over here. Let's skip that because it's the same as in the lecture. See, in this program, I first defined as a function my f vector in Python code. You have first line, second line, third line. It's the same as the lecture what we have here. Same formula here. What about the next part? I have then defined my inverse of the J matrix. Okay, that's matrix. Then I set my initial guess. And then I print out the value just to report the value. And then I have this update. For the updating in Python, let me zoom in to show the code here. The command is this, matmul. That as a Python subroutine for multiplying metrics together. In this case, we have this inverse J in the front and the vector here in the back. So you multiply them, then subtract it from the previous R value, and then update. So let me do the calculation and then run the calculation. Okay. Well, it's gonna take some time. While we waiting, so how do you like the music? Is it good? Do say something because I don't know if the internet has been disconnected or not. Okay. Yes. I don't hear anything. Okay.
Yes, Ajahn.
Okay. I was wondering if my internet has been disconnected. Okay, thank you. I forgot every time we have this participation. That's for Dishin and the other one for Dewey. Okay, for warning me. Now let's hear in the beginning. In the beginning, we have this initial guess, 111, and then as it proceeds through its iteration, it only takes 5 iterations to converge to a single value, 1.4, 1.4 something. Okay, that's actually the exact answer. The answer for this is root of 2 for the x and the y, and a 0 for the z, which you can see this very clearly in the beginning. I mean, if you can kind of see the answer right away if you go back to the, the equation here. See there, z is 0 from the middle equation, and y and x has to be the same. So we go back to the first equation. You have this x squared plus y squared is 2 squared. That's 4. So we have a circular equation. Okay, and x and y must be root of 2 in this case. All right. So as you can see, this is how we do the root finding for many variables in this case. Okay. Now that's the summary of the output. Okay, and I hope you can follow this nicely. Okay, that's just the warm up part of the optimization. Now let's go to the topic of today: optimization and root finding. Now these two topics are related actually. Let's begin with this nice formal way of putting the problem. Suppose we have a function, just one variable, e of x, which we seek to optimize. Okay. Now at this optimum value of this here, okay, what do you think is the condition at the minimum? Does anybody know? I remember learning this when I was in Matayom 5, or I guess in English it's 11th grade in high school. So what is it? What do you think is the condition, a calculus condition for this minimum value of the E? Now, E can be any value, anything, profit, or a cost, or a energy. Anybody? Let's go back to my Microsoft team. What is the mathematical condition which defines the minimum or a minimum of a function? If you look at this graph here, something is very special about the graph at this minimum point. What is it?
The slope is equal to 0.
Very good. So we have this very faint. I need to give you an applause. Okay. Very faint answer from I think Dewey. Okay, that the slope must be 0 at the minimum point. You see that slope is 0, so we can put that here, that dE dx is 0 at the minimum. And then for convenience, to make the notations much simpler, I can define a function. Let's call a function f of x and define it as the first derivative of e. Okay, so f is e prime. Okay, now let's go back to the condition for this minimum. We have then, by this definition, fx is 0. Well, we go back now to the root finding problem now. So we can use all the tricks, all the techniques that we have studied in the root finding to solve for optimization problem, okay, using simple definition like this. So how do we find minimum value of the E? Okay, well, if you recall, if you remember the Newton's method for root finding, we have this updating scheme. The F in the upstairs and F prime downstairs. But we know that the F is E prime, so we can turn this into optimization problem. F become E prime, F prime becomes E double prime, just like that. Very simple, very simple. Now we know how to find minimum point of a function that you want to minimize energy, the cost of your business, and so on. Now, before doing the example, let's make it bigger by looking at many variable cases. Okay. Now, suppose my function, which I want to optimize, has many variable, like cost of doing business, depends on many factors, depends on salaries of the workers, depends on the taxes, on many things. That's like in this case, the E or the energy of something depends on the X, Y, and the Z. And if you look at this picture using your eyes, you can kind of see that the minimum happens there, right in the middle of this shaded color here. The condition for this is very similar to the one-dimensional case, very similar here. But now we have three dimension or more. That is the case. Okay, you have d dx, d dy, d dz, and all things here must be 0 for this case. Now we do the same technique. We define now a vector f, which contains all these derivatives, x, y, and z. Okay. Now, in calculus, we sometimes use this symbol, this upside down triangle with the arrow here. This thing is called the gradient. We call it gradient. It means this, okay? Derivative of that value respect to the x, y, and z, and all the unknown involved here. So we define f as the gradient of the E value. Okay, what do we do next? And at minimum, then we can rewrite this equation in a very compact, very small and compact form that vector f is 0. Okay, well, now we go back to the previous root finding problem, but for 3 unknowns. So how do we do it? Well, do the same trick as before. Before we have this nice Jacobian inverse multiplying to the f vector, and we can turn that into this particular form. Now, the f, still the f here, that's the f vector, but sometimes we write this as the gradient instead, just to make it more sophisticated, but it's the same meaning. Now, the matrix J, Jacobian, is first derivative, will be turned into the matrix H, which is a second derivative matrix, defined as this one. Okay, now that is how you do it. Let me go back to the one-dimensional case just to see the analogy of this here. Okay, in 1D, we go from f prime, the first derivative, to e double prime, second derivative. In the same fashion for this x, y, and z, we go from the Jacobian, the first derivative, to Hessian, second derivative matrix, defined this way. Now, well, it looked a bit scary to compute this because it's huge, and you do a second derivative, it's complicated. But at the end of the lecture, I'll show you a way to avoid computing this h altogether. Okay, but let's go step by step and see how we do it with this process first. An example, okay. Suppose I have this very nice function of e. I have an, let me see here. I have an assistant come to get a, good morning, good afternoon, come to get a telescope. Where's that? Oh, now it is. Let me show you this a little bit here. I just got a new telescope. Very nice big one. It's Orion telescope. Okay, here, over there. Very expensive. Okay, but I hope to find something cool in the sky. Okay, maybe I can find some new stars or nice holes in the on the moon or something. Okay, so let's get back to the example of the optimization. Suppose I have a function like this. E depends on x and y, and it is that particular function minus cosine x and cosine y. Now we know from the graph, just look at it visually, that the exact answer is at here. The x and y is 0 at this point. The graph becomes optimum or minimum here, okay? But let's try to use this numerical method to solve for the answer, okay? So what do? We need to compute the gradient or the change of the e value defined by this way, dE dx and dE dy, okay? So let's do that. If you do the derivative, dE dx, cosine x become minus sine x, and the minus there cancels the minus in the front, so you get plus sine x. The cosine y is still there, okay? It does not change because we are taking derivative with respect to x in this case. What about the dE dy? It's the same kind of concept, but now we let's call it diff to make it simpler, okay? It's take too long for me to say some derivative. We diff dE dy, then the cosine y become minus sine y. And that minus cancel minus here. You get the plus there. So we have sine, and cosine still there. It does not change because we are diffing respect to the y value. Now, the next ingredient will be somewhat complicated to do, okay? Let's give my students some time to look at it. Let's so I have this I have a chance to sit my drink. We have 4 participants. Let's say Dishen do you do this dE dx square, and Panda with the dE dx dy, and then was a Patrada, you do the diff respect to the y square, and then give me the answer. Okay, tell me when you're ready. I can't really hear this, okay, but I think I've tested. So you're ready. What about the upper left corner of the matrix? dE dx squared. What do you get? You already have the dE dx. If you diff it once more time. Yes?
Cos x sin y.
Very good. I shouldn't give you all the answer. Cos x sine y, and then for Panda, you should get this, right? You should get this sine x sine y with a minus sign there, and it should be the same value for this and that for the off diagonal over here. And for Patrada, you should get the same diagonal element. So that's very simple. You can do it by hand. But for very big matrix, And I can tell you that in the real engineering applications, or when you do quantum mechanical calculations and so on, the dimension of the unknown is huge, about 1,000, about 1,000 by 1,000 metrics. That's very complicated. Let's ask Padrada, because she does all these quantum calculations all the time. So Padrada, what is your dimension of the metrics that you do in your research usually?
Two-dimensional?
Yes, but the number of elements, the number of the size of the matrix.
Oh, I use n equal, I forgot that, 100 multiply 100 around.
So you have this 100 by 100 matrix element. Okay, maybe your computers is not that big. Usually we do 1,000 by 1,000. Okay, then it's going to be very difficult to find a Hessian. But at least for this example, we can do this by hand. Okay. Now, what about the what about the inverse? The inverse of the Hessian is going to be even much more complicated. Now, in fact, I can tell you the following. Even though in quantum mechanics it's difficult to find the Hessian for, say, 1,000 by 1,000 metrics, people still do it today because, just because to be precise. But the inverse is hopeless. The inverse is hopeless. You cannot begin to imagine doing a inverse of 1,000 by 1,000 matrix by hand. Okay, that's not possible. So in this case, I use Wolfram Alpha to do the job for me, and I got that result. So thank you, Wolfram Alpha, for this nice free software for education for all mankind. Okay, now you can pick gap. Let's say 0.25, and then we can compute the gradient vector by using that formula before. Let me go back to there. Here's my formula of the gradient. So we compute that gradient, we compute the inverse of the Hessian, and then we use that updating for optimization, and then compute the R1 and R2, R3, and 2 convergence. Okay, so I have the code for you to see. But before going to the code, I have quizzes just to check the understanding, okay, of this exercise. You can try, see what happens if you try other initial guesses, like 0, 1, 0, 2, or 2, 2, and try to see what do they mean, okay? What type of stationary point are these? Are these minimum, maximum, or something else altogether? And how do you know that? You can need to learn how to plot a graph for that here. Okay. Now let's go to the code that I have prepared for you. Okay, for this section. Let's look at the big picture of the code. Okay, zoom out first here. Now that is what we have here for optimization using Newton's method. I have to define my gradient, which over here, that's how I define my gradient vector. I have to go to my scratch paper and then, do some hand calculus things, working on this magic of calculus. I get this G vector gradient. I have to use some kung fu for the mathematics to find the formulas for the inverse of the Hessian, but I put it in there. So in the beginning, let me zoom in just to see it better. I pick initial guess right there, and then I just keep updating. I compute the gradient vector, compute the Hessian, and then multiply to each other subtract that from the previous value, I get new one, and I go in cycle this here. If I click run this code, that is the answer. So it goes to the answer very quickly. Only 5 iteration or 4 tops or 4. Okay. Now, see, the quiz told us to change the initial guesses. Okay, let's do that. I have so what was that? I forgot. I don't want to go back to the screen. So what was the initial guesses for the quizzes? Can anybody tell me?
02, I remember.
0.
2.
The 0. The first is a 0, 1, right?
Yeah, it's 0, 1,
So,
Okay.
yes.
2.
Let's try this one first. 0, 1. You pick 0, 1. What do we get? We go back to the same answer as before. The exact answer is at the 0, at the minimum. Okay. Now, suppose I go to 0, 2. What happens then? Click run. Oh, now it goes to something else. It's not 0, 0 anymore, but something else. So this must be a new, what we call stationary, okay, point. Okay, some kind of. So what would be the? Can you guess the value of this? 3.1415. Is that pi? Okay, very good. That's a pi. So the answer is, for this case, is 0 pi. Now it's a different thing. The last choice of the initial guess is 2, 2. I go to now something different here. 1.57. What do you think that is? And I can, give you the answer from Google. What do you think? Can anybody guess what that is? We do this all the time in physics. The what?
Over 2.
Let's try it. Okay. I don't know if the answer is right or wrong, but just to give you an applause just for saying something. Pi over 2. Let's see if that's correct. Very good. So we have this pi over 2 over there for this type of answer. And now the quizzes ask us to investigate. Okay. Now you do this all the time in physics. As a researcher, you need to try to find some way to understand what happens. You have 0, 0 as the answer. You have 0 pi, another answer. You have pi over 2, pi half for the last answer. So what are these? By plotting graph. Now you are a student now, so it's good to try some new things. Okay, we have learned a lot about Python and Google Colab so far, and I want to show you some new software here, just to get you acquainted with new things, new stuff. An octave. An octave can give you a very nice graph. Let me see if I can find the file here. There you go. I have doc nodes octave. Okay. There. I hope you can see the code easily, because it is usually very small. How do I zoom in with octave so that you can see have this view or zoom in? Let's try it again. Zoom in again, again zoom in, and zoom in. There you go. So that is the code for octave. You should try it. You can cap the screen for this moment of the lecture, and then do your own programming. I can put the function that I want to plot in 2D right here, and then see what happens for these here. Let me change the font size to make it bigger to 16 font size. I click run. I get that. Okay, very nice. I can rotate I can rotate the graph, and you can see that in the middle you have a minimum, 0, 0 there as the mouse is pointing. What about 0 pi? What about the pi? 0 pi. What about 0 pi? What are they? Is another minimum here, right here. Okay. What else do we have? What else do we have? We have
Pi over 2.
pi over 2 and pi over 2. What kind of point is that? Is that minimum? You know, if right there, if you look at the curve of the surface from this angle, it's not minimum. You see, it's maximum, this angle. Do you see there? 1.5 something. But if you look at the curve at another angle, it's minimum over here. So it's neither minimum nor maximum. So what is it? What is the name that we call this kind of in-between point? Does anybody know? There's a special name for it. That is neither maxima nor minima, but it's something in between, both even. You just look at some different angle and you see this. With this angle, it's maximum. With this angle, it's minimum over here. So
Is it constant value?
the what?
Constant value.
For must not. I haven't heard of that name before. It has to do with a horse. With a horse. Anybody? It's called.
I'm not sure, but is the name the same as other like parabola? Is it vortex? Is it
Vortex. It's not
vortex?
not
It's a
vortex.
saddle point.
Vortex is a spiral. Yes.
This is a saddle point.
Saddle point. Very good. Let me give you an applaud for that. The name has to do with a horse. Let me go here. And saddle, HORSE. Okay. Images. Come on, there you go. There's a saddle point there. Okay. The thing that you sit on. Okay. It's neither maximum or minimum. If you look at this, in this way, it's minimum. Look at the other way, it's maximum. Okay. Now, if I used mathematical term, you can see the graph of this saddle point quite clearly. Let's go on here and surface, FACE, saddle surface. There you go. That's saddle point surface. Okay. So it turns out that this method that we call Newton's method can give us all kinds of stationary point, not just minimum, but maximum sometimes, but also saddle point, things in between. So you should not just use the software to get an answer. You should also analyze the answer to see what happens also. Okay, so that's the exercise for this. Now before we get into the climax of the optimization over here, okay, I hope that you're doing okay with the math and all that. Okay, now let's go to the climax of the optimization. Now, as you see that the Hessian matrix is very difficult to calculate. Okay, and you can have to use some software. When you have 1,000 by 1,000 matrix, it's almost impossible to find the Hessian by hand. Okay, so what do we do? It happens that we can compute the Hessian using numerical method, and it's going to be very fast. Okay, very fast. Okay, compared to analytical, and the answer is almost the same. Okay, very perfect, very amazing method. But before I show you how to compute the Hessian using numerical method, let me rewrite this inverse first, because you have a lot of like notations, and it becomes very dirty notation if you don't do that. So let me define the inverse of Hessian as another matrix. Let's call it K matrix to make it simple of formula for us. It turns out that 4 guys, I think it's about 50 years ago, came up with this formula to compute the inverse of the Hessian or the K, okay, using just updating scheme. So you don't have to compute the Hessian analytically. You just update the Hessian, or in this case, inverse of the Hessian, okay, using that formula here. Now we will not have time to prove this formula. I think the name is BFGS or Broyden, Fletcher, Goldstein, and Shannon. Okay, BFGS, I think. So I'm going to show you instead the process of doing this updating scheme, and we'll see how the input, how the results compare to the previous case where we use the exact analytical Hessian. Okay. Now, you know, the formula is a little bit scary, but at least it's not as scary as that Hessian here. Okay, this one is very scary. Imagine 1,000 by 1,000 metric is huge, is huge. Now let's go with term by term, see what happens. Okay, now let's compare the speed of the two methods. On the top, we have a simple Newton's method. We have to compute the inverse of the Hessian. Okay, now that's also a slow process because the function of complexity is n cubed. Now we talked about this in the previous lecture about this complexity function. It tells you the cost of computing power that you need to do this calculation. In this case, is n cubed. N cubed, what does n cubed means? It means if you, let's ask, I imagine that I asked Patrada this problem last week. Let's ask her again, see if you remember. For n cubed complexity, if I double the size of my matrix, you know, from this, make it double the size of my matrix, the cost of computing power will be increased by how many times?
8 times.
Very good. Another applause for this here. Okay, even the real applause there. Okay, now you're very fast and very confident about your answer. Now, for this quasi-Newton method, we don't have to compute the inverse directly because we keep updating, and therefore the whole thing becomes just matrix multiplication instead, and that O function is O squared. Now, if you compare n cubed and n squared, that's n difference. What does it mean? It means that for, let's say, for Patrada's research work, she said in the beginning of this lecture that the n is about 100 by 100, and therefore the quasi-Newton is about 100 times faster than the Newton method. 100 times faster is a lot. Suppose it takes her a day to do quasi-Newton. For Newton, she would need 100 days, 3 months. That's a day and 3 months comparison. So it's huge differences between these two. Now, if you look at, before going to the example, if you look at the properties of this quasi-Newton, you see that we just need to update the k, keep updating. We only need this multiplication, so it's a lot faster. And we only need the first derivative. Why? We still have to compute the gradient for this method. Okay, that cannot be avoided. Still need to compute gradient, okay, for this one. Let's look at the steps in the beginning. Just like before, we need to define the function, okay, of E. We need to know that, and then compute the gradient vector. Now, just stop here a little bit here, just to give you an insight about other kind of optimization method. Okay. Now, in some other applications, we do not know the actual function of E. Maybe we are looking at the stock market prices, and then we don't know the function of that prices. We only have a bunch of dots and data points, and therefore with that application we don't know the function E. Then we cannot compute the gradient in this case. What can we do then? Is there any idea how we can do that? Now, there are other optimization methods called, I think the most popular one that I know is called simplex, S-I-M-P-L-E-X, simplex method. And that method can find you the minimum without the need to compute the gradient. Okay, if you don't want to know more about that, look on that on the internet. Okay. So let's get back to what we have here. Suppose you know that function, you can compute the gradient, and you pick initial guess, 1, 1, maybe a 0.25, 0.25, or anything that you want to pick initial guess of that vector. Now, you might think that, well, you can keep updating the k, but at least you need to know the initial value of the k. Okay, and how do we do that? There are two choices here. The first choice would be to compute the Hessian at that starting point, then go with the inverse, then you know the k at the initial point. The second choice of this here, which people do all the time, which is very popular, is to simply set the k to identity matrix, just like that, just for initial value for k. In the subsequent value later on, you will get some, better k value, k matrix. Okay. Now we simply update the vector. You get closer to the solution, and you compute this DRDG, and in the BFGS, it tells you what these mean. But compute the DRDG, and then you get the new k vector. Then you go back to the number 4 step, and you go in cycle like this. Okay, very good. I'll show you the code exactly just in a minute, but let's look at this notation of the updating scheme first, okay? Because it is a good time to pause a little bit. Let's go slowly and look at the matrix vector notation and review what we talked about in the last lecture. Now that is BFGS. Again, Broyden, Fletcher, Golden, Ghost. Oh my God, I should not just guess their names. That would be impolite. BFGS method. Okay, so exactly forgot. Broyden, Fletcher, Goldfarb, and Shano algorithm. Very good. Thank you for your wonderful work for giving us 100 times faster optimization problem. Okay. Now, this is what their formula looks like. We have some previous iteration of the k vector, k matrix, and you do this you get the next cycle of the inverse Hessian or the K matrix. Now to do this calculation over here, you have a bunch of matrix. What we know already is this: the I, that's very simple. That is identity matrix. Okay, sorry for this microphone resonance. And then the alpha, if you look at previous formula, it's just a dot product between two vectors. So you know how to do that already. What about this weird, strange symbol here? Okay, we have a vector multiplied by a vector transpose, a vector transpose, a vector, and vector transpose. What are these things? Now, if I make it more general and consider this here, you have a vector u, any vector u, which is a roll vector, like this, like a bamboo stick, like this. Okay, multiplied by v transpose. Now this will give you n by n matrix instead. We'll see what happens here. On the left panel, we have the conventional dot product. We have a vector v, a bamboo stick, okay, 1, 2, 2, and u transpose. Transpose means you twist the thing 90 degree, okay, like so, 90 degree. So you have that in the horizontal axis, say for example 2, 0, 1 instead. Now when you multiply these two things together, in the beginning of the previous lecture, I told you to imagine in your head, pick that up, rotate it, and then couple the elements, multiply them, you get 4. Okay, let's do it again. Let's do it again. Here we have 1, 2, and 2, 0, and 1, 2, and you get 4. That's a simple dot product, okay, of the vector. Now, if I swap the order of the transpose, now I have this v transpose on the right instead, and u's on the left. Again, the u vector is the bamboo stick, vertical stick. But t transpose, you twist it 90 degrees. Okay, you got that here. How do you do this multiplication? Well, the rules still apply in here. You imagine in your head this green column, you twist it and multiply it. Okay. Let's do the first element. Okay, we have this 1 here, and then you twist that and couple with the number on the left, you get 2. What about the next row? You get 0 in here. What about this one? You get number 1. That's how you do this kind of multiplication. You move on to the next column. This column in the middle here is middle here. Then you just keep doing the same thing. You multiply these two to the vector on the left. See there, there. Okay, and let's do it again in one step, in one shot. 4, 0, and 2. Okay, very good. Now the last column, you move to the last column, and you just do the same thing. 2 times 2 is 4. 2 times 0 is 0, and 2 times 1 is 2. So that's how you do this kind of strange notation of u and v transpose. So you get matrix subtraction. Subtract this matrix from the I, subtract that matrix from the I, multiply them, and add another matrix here, and you get the final value for the K. Now, I can give you a very nice formula for the resulting matrix. Say U times V transpose is A matrix, and the element Aij is the multiplication of Ui Vj in this case. Okay, now let's go to see the code in Python. Okay, a little bit here. Google collaborations. Let's zoom out to see this big values there. Second here. Very good. Now we have this climax of optimization, which is the quasi-Newton. Quasi in this case means not quite. It means similar but not the same. Okay, not the same as Newton. Some adapted version of the Newton method. Now, in this code, it's going to be a long. Let me not that long really. It's if you look at it. For example, I have this subroutine that's called forming a matrix. I put this u and v as the input vector, then I compute the matrix using that formula as described from the lecture over here. Now, in the BFGS method, I need to know all the gradient and the values, and I update it. I will leave it to the wonderful student to investigate further, with this code, because now you are a senior researcher. You are capable of researching something on your own. Let's go back to the answer here. Now, if you compare the output and the code, you see there in Newton method, I have to define in the code the inverse of the Hessian in this case. Maybe it's difficult to see, but you can see there, which is going to be difficult to find. For the quasi version, I don't need to do it all. I just compute the gradient, which is easy. Okay. Now the output is almost the same in case of convergence, but the value will be different. Like for this here, you have minus 0.02, but for this quasi version, you get plus 0.01. So the value will be different, but the result in the final is the same. And the convergence is also the same, speed. Okay, so it's very good. Very good. So thank you, BFGS. Again, Mr. Broyden, Fletcher, Goldfarb, and Shannon. Okay, they have done very good service to the. Optimization has been used in all kinds of applications. From space exploration to engineering to marketing to all kinds of things, and their method makes the world a better place. Okay. Now, at this point, do you have questions or comments before we take off from this chapter and go to the much more exciting concept of partial differential equations? Any comment at all?
I have a question, sir.
Yes.
Yes. So basically, this the what is BFGS thing. So basically, it's kind of like sure is that the point that you will get at the final step will be the minimum.
No. Actually,
is that right? Because of like over here, you start with the identity matrix, which is 1, 1, okay. And then you get 0, 0. But it's previously, I suppose, if you go to the plot of 1, 1, you have another point. I suppose this is like saddle point or something.
Very good. Let's try it. Let's see if this BFGS update can take us to some other kind of stationary points, saddle points, maximum, and so forth. Let's say 1, 1. 1, 1. What do we get? So this is the last one. If I use 1, 1 as my initial guess, I go to this wild, things. I don't get any answer at all. I just go and oscillating. If I go to 2, 2, just like before, and There you go. You got a saddle point. You get saddle point here for 2, 2. And let's say 0, 2. Would it be maximum here? Okay. Very good.
So you get it's not like that. I mean, that's stable compared to the Newton because of the Newton. No. Because of the Newton, you can get by like a 4th iteration, but this one you cannot get it.
Very good. So it's not that stable. Okay. Very good observation. But also, even for Newton method, you can get all kinds of stationary points, which we don't know what kind of point that is until you plot the graph or do some further analysis. Like this will be more advanced, like you're looking at the eigenvalue of the Hessian matrix and so forth. Okay, but these are all the things that you need to keep in mind. Oh, I forgot. Thank you to bring that up. Okay. Keep in mind before you're doing this integration, there's no magic formula to give you all the answers. And at the end, you should be the one who investigate and always check if you get the right answer or not. See, last week, we even found out that the Python code in Google Colab or in Python code give you the wrong eigenvectors with the sign go plus and minus randomly. Okay. And you will not see that behavior in the LAPACK or C or Fortran library. I checked already. So very good. You should always check this answer. You see that here, you 1 here. You get weird. You don't get the answer for this case. Okay. So that's kind of not. It makes your life more exciting. That's what I am saying, okay? It's because you want to check, you need to check all the time. Very good. Okay. Now, I need to go, let's go to the next topic. Okay, put some soft music there because the next topic is going to be very exciting. And also a lot of strange mathematics. Okay. So let me close this window and okay. By the way, this is very nice. You should try to play around with this octave thing. Okay, close this, and I have that prepared. Oh, I still have this nice story from the Feynman's lecture of the first day of physics for you also. Okay. So, well, welcome to the world of physics. And there are all kinds of equations in physics. I mean, it's so many equations in physics, and you look at it, you cannot absorb it all. Just so many of them. And we are going to look at those examples of the equation, and we call that usually partial differential equation, okay, with the 3 examples of first, second, and third, okay. Now let's just give you a scary picture of those equations in physics, which I have prepared for you, okay, huge over here, very scary, and there's just a very small subset of what we know in physics. Very complicated, and at least if you look at this PowerPoint presentation here. But it is, I think it's customary that when you look at all kinds of equations like this, you should hear a story. I mean, these equations always have to be accompanied with a perfect story told first by, I believe, Richard Feynman's lecture in physics. Maybe you have that at home. I have that 3 books in my office. It's great. So this is a story about that should go along with so many equations here to give you an overview of what physics is all about. the heart of physics. Okay, I am proud to tell you that, just to relax a little bit for this exciting presentation. But first, let me put a. There you go. Okay, so are you ready for this bedtime story for your children, Dishan?
Yes, Ajahn.
Okay. So just imagine Dishan, she has children, and she wants first impression. First impression is the key to everything. The first time we met someone, the first time we met something, this first impression gives us the guideline of how we deal with this topic, this something, all the way down the road in our life. And Dichen wants her son and her daughter to have a good feeling of physics and have a good understanding of what physics really is and what it's all about. After all, her kid's gonna see all the equation down the road in their life. Okay, so what is that story of the first time that a person should hear when she or he hears the word physics? Okay, all right, the first thing, the first impression of physics. Suppose your heart is broken. You know, maybe your heart is broken. Suppose he or she's leave you and go somewhere else, and you are feeling very sad in this moment of this lonely night, and you walk along the beach like so, and you on the beach you see all the sand around, and underneath your feet, sands around you, millions of grains of sand all around you. And you also see this bunch of rock on the beach there, on this black dot here. You walk there, you see this wave coming, and you shout or you sing a song, this sad song that you heard before, to the sea. And you see that moon in the sky, and you see the stars in the sky. So that is life. Okay, life is very complicated. Anywhere that you look around you, in your room right now, you see these walls, you see these items, you see this curtain. You know, life is always full of so many particles and system and stories and love and sadness. Life is complicated. What about physics? Now, about 350 years ago, a guy by the name of Isaac Newton, he found that you can kind of understand the motion of a rock by that simple equation. Okay, F equals ma, and that's rock. Now you can see and predict exactly and precisely how the rock's going to move, how far it's going to go, how long it's going to take to fall, and so forth. But then you'll realize that the sands underneath your feet are also a bunch of rocks. Very small rocks, but still rocks. And therefore, you can use the same understanding, the same equation that you understand the rock, to understand the sand, the grains of sand. Now you look in the sky, you see the moon. The moon is also a rock, a big rock, but still you have the rock. And therefore, what you have understood about the sand and the rock applies to the moon. Now, the same equation can be applied to the stars in the universe, because stars are a bunch of giant rocks or clouds of objects. And you see that the universe then is encompassed by a single equation. And that means that physics is simple compared to life, because you only have one equation that you explain all of them in the universe around you. Of course, as you go on to the physics, you know that there are also other kinds of things in physics. You have wave, the sound motion, the wave motion, you have particles, the field, you know, and so on. But still, compared to life, physics is very simple. So don't let anybody tell you that physics is hard, complicated. Life indeed is complicated and physics is simple. All right. Now at this point, I think I should give me an applause for this wonderful story. Now you can read more about this. Story from the Feynman lecture. I believe this is in the introduction section of his first book. Okay. Now, so look at this equation one by one. I can split these equations into three categories depending on the variables that involve in the equation. We have space only. It means that in this equation you only have x, y, and z, or the space, and that is Laplace equation. We talked about this in the previous lecture. Now the Laplace equation, that's mathematics, but the physics involved can be in many subjects or many branches of physics. You have the same Laplace in electricity, the same Laplace in the ideal fluid equation. Okay. Now the Poisson equation is somewhat more complicated. That on the right hand side is not zero, but contains something. We call this the source of the potential. Okay, the source of electric, the source of gravity. Okay, or if you move to the next category that contains the space and time, but time only have the first derivative. That's an example of the Schrödinger equation. In quantum mechanics, diffusion equation, you know that these two are the same, at least in the structure of the mathematics. You have the first derivative of the t on the left hand side. On the right hand side, you get the second, the Laplace operator. But for the quantum mechanic, you have this I number, which make the whole things more exciting. Okay. Now, the thing that we are going to talk about in this chapter are these three sub-equations. We have what we call the continuity equation, or in Thai, we call this สมการความต่อเนื่อง That's in Thai language. That will be the very first Thai word I talked about today. Okay, I hope it's okay. And that is also similar to this equation. On the left hand side, you have only for derivative. On the right hand side, we have some other things here. Okay, Navier-Stokes equation, that is very big and messy. Okay, very scary. We'll talk about that in this chapter. And at last, the wave equation. In the wave equation, now the wave equation is different from the rest of this equation. Namely, on the left-hand side, we have the second derivative instead of the first one here. So this gives you a different kind of behavior of the solution, which we'll talk about this in this chapter. Okay. Now let me switch my movement a little bit. So let me prepare for the next PDE. Now, we should try to understand beyond the mathematics the actual meaning of this equation, namely the continuity equation. What do they mean? Okay, now we have three terms in this equation: the left-hand side and the right-hand side. What do they mean? Okay, I can summarize the, oh man, okay, my hands. I can summarize the big picture of this equation using that animation here. On the left, we have a box. You know, just imagine very small and tiny boxes, small volume. And I want to focus on something that's inside the box. Anything, liquid, gas, pigment of colors, something, you know, like particles, chemical particle that we can smell, you know, and the increase of that thing is getting more and more and more and more and more and more is equal to only from two ways of increasing the amount of something on the left hand side. Okay, let's look at that animation. Okay, on the left we have something that's increasing. It's getting more and more and more, maybe water or something. Now this comes from two ways. First, it must flow from outside into the box, like that. Okay, and additionally, it can also be generated from the inside the box. These two add together give you the total increase of that thing over time. Anything, gas, liquid, or something. I don't know. Okay, now let's pause the animation over here and try to understand the terms involved in this equation. On the left hand side is easy. Okay, we have d rho dt, that is the increase of that thing over time. What about this term on the right hand side, the j? That's what we call a flux. A flux, what does the flux mean? A flux means the amount of things going through the surface, going through. If you have this huge flux go very fast, a small flux, slowly going, that's flux. Okay, the amount of something going through a surface, anything. Now, if we take what we call divergence, what that means in simple language is that the amount of something leaving the box. Now, if you compare these two meanings, the flux involves any surface that you can think of in general. But divergence make the meanings more specific or narrow. Not any surface, but only the surface of the box, the small box. And by definition, it's the amount leaving, okay. But from the animation, we are talking about the flow inside the box. And therefore, we put this minus sign here to flip the meaning of the divergence. Now the whole thing on the right-hand side, in the first term, means the amount of thing going inside the box with the minus sign over there. What about the last term that we have? The last term is simply a function of generation rate. Okay, anything. Sometimes things don't have to come from outside, but also being produced by the box, the thing inside the box. Let me give you an example. Okay, this very vivid example. Suppose I'm sitting here, and I detect an increase of something. The smell is getting very bad. It's like a citric acid. It's like some very bad gas smell. An increase of the smell of the gas molecule. Then I look around to see where it's coming from. Does it come from the walls, the windows, the door? And it turns out that the door is closed. The windows are closed. Therefore, the first term will be 0 in this case, in this example. Though that's the case, it must come from inside the room. For me, maybe I'm the one who are pumping out this bad smell gas. Anyway, and that is the sigma term. Okay. So that makes the meaning very simple for this equation that we call สมการความต่อเนื่อง or continuity equation. Okay. Now let's look further into how we use this equation in physics. Okay. Now you are going to see in this lecture so many monsters in calculus. You're going to see gradient, divergence, curl, vector field, scalar field, and tensor, and so forth. We're going to talk about this in the next chapter. Okay, but for now, we focus on the meaning. So do enjoy a lovely tour for now. Okay. So how do we use this equation in physics. Many ways possible. We can have what we call conservation of charge. If you think of the charge and we say, oh, the charge is conserved, it means that the charge cannot be destroyed, cannot be created. It must be the same amount over all the volume. What that means in the mathematics is that the last term is always 0 in this case. So for this case, we set sigma 0 because the charge cannot be destroyed nor created. And we are left with simple two-term equation here. Now J in this case is the current density of the charge as it flows from the system inside the wire, for example. We can also have what we call conservation of energy. A very simple concept that the energy can only transfer and change forms, but cannot be produced. Okay, and that's how we do it in mathematics. We set the sigma 0 in this case. We get that equation. Okay, what about this fluid dynamics? In fluid dynamics, we talk about how the flow of the water, of the gas, of liquid, and so forth. Now, the flow of something can be thought of as two factors: the speed of the flow, the V, and also the density of that material. If it's dense, then the flow is huge, okay, and so forth. If you plug that into this equation of continuity, you get that equation here, and that gives you the equation of the fluid dynamics. Okay, again, if we imagine that the fluid does not leak away, it's conserved, that means that the sigma is 0 in this case. The last example is diffusion equation. Okay, now we learned about this in the previous lecture, but let's look at diffusion from the perspective of this equation instead. So we have this diffusion, the color pigment or the gas molecule, it diffuses from this high concentration to lower regions, from here to there. Let me give you an example of the density of the color pigment. Suppose here we have high density, very red color. Here we have this low density color here. Now it's going to diffuse from here to here, go there. But the speed of the diffusion depends on the gradient of the density. If you have a huge gradient, it diffuses very fast. If you have very small gradient, diffuse slowly. Okay, and that's why in the beginning diffusion occurs very fast and then becomes slower and slower and stand still at the end. Now in mathematics, we can set the current as this gradient of rho and d and minus here. We plug that in to this equation, you get that here, and the minus and minus become the plus, the d come to front, and you have this divergence of gradient. Now in the next chapter, we are going to do this kung fu of the vector calculus, and we'll see that this here becomes Laplacian operator. Now we get back what we have as the diffusion equation in the last chapter as before. Okay, so that's how we use this equation in physics, but we don't solve it normally. We use it to build another equation. Okay, we are getting to a very end of the this lecture period. Okay, and then you see why in a moment. Okay, that's the monstrous equation, Navier-Stokes equation. This equation tells you how fluid moves, and it's also one of the 7 wonders of mathematics. What do I mean by that? Okay, long time ago, a group of mathematicians come together and decide that there are 7 problems in mathematics that is very important to solve, but unsolved. Okay, and they put an award, a reward for $1 million for each of these 7 problems of unsolved mathematical equation. This is one of them. Okay, the Navier-Stokes equation is one of the wonder in mathematics. You gotta have to prove something about, which we'll talk about this in the next lecture, what that will be. But this is what it looks like, the Navier-Stokes equation in a compact form. Even in a compact form, it's long. Okay. Now let's look at the expanded form. If you expand the term here, what do I mean by that? If I call the speed of the flow, as the liquid flows, it has a speed of the liquid at any point. If I call the component of each velocity u, v, w, okay, I have 3 equations for each axis of the speed. I have that for the x-axis, and that for the y-axis, and that for the z-axis. Very scary. Okay, that's why this one goes with $1 million prize of the mathematics here. Now, you may look at this equation and say it's very complicated. It's not. Okay, the structure is very simple. Now let me show you the structure of this equation. What that really is here is a Newton equation for the small element of liquid, a small droplet of liquid. And that equation here tells you simple second laws of motion, the F equal ma. Now that's not the actual force, but rather the force per unit volume in this case. You can kind of see here, for example, if you look at the left-hand side, the mass divided by volume, what is it? Let's wait for one of my brave students to answer me.
Density.
Very good. That's rho. That's rho here. That's why you have rho on the left-hand side of this equation. The A is acceleration. That is the derivative of the speed over time. That's why you have this du dt here, okay? But there are some other terms which we'll talk about that. But in essence, it's simply F ma, okay? What is this F here? Sigma F means you have so many forces in the term. Well, you get the first term is the force of gravity. As liquid move and flow, you have this mg, okay, mg. The mg, the m energy, the m divided by volume, you get the rho and g over there. And also the force due to the pressure difference, because you have this high pressure, very high pressure, and that small pressure is going to flow from left to right in this case. And also viscosities, also the ความหนืด in Thai language, give you the last force in this is a very simple version of Navier-Stokes also. So anyway, since we are talking about this huge $1 million prize equation, this equation is not something you talked about at the end of the lecture, because you're going to be very tired. So let's say that we should stop here first for this lecture, then we can start fresh in the next lecture. And I'll show you all kinds of animations, all kinds of numerical solution, just to give you an idea and how to solve it, actual Navier-Stokes equation. Okay. Now, before I take off with this period of lecture, do you have any other requests special requests for me to prepare this exciting lecture for the wonder of mathematics that's called Navier-Stokes equation. Any request that you want to make? Or any other comments that you want to know? Then we're going to go to the wave equation. You know, a wave on a water surface, gravitational wave of the wave. That's the second derivative of the something over t squared, over time squared. Anything? Oh, I forgot. I think the person who requested Navier-Stokes was not Dewey. Was it? It was the other person from Japan also. What was his name? With the T. Oh shit! Is he here with us? Oh, maybe he will join us in the YouTube. Okay. So Tosapon, if you here with me, you know, in YouTube, you know that I have fulfilled your request. You know, just give me an applaud or click share and like the video. Okay. All right. Before I take off, in this lecture, do you have any other comments about the homework problems? I'm sure you have learned so much in this. How many of 7? I think it's 7 lectures already. And it's very intense class, and I do encourage you to go and try to work on the Python code, okay? Or maybe you can do your own programming in using C for DChain. For Pattern, you can do your MATLAB programming. You can use my code as the starting point, but do your own things. And even if you cannot do it here or now in this semester, you can do it later on in your life when you have time, because it's going to be very good experience for you to practice. You know, you listen to me doing things, you're not going to be good at it because you have to work on it to be good at it. Just like eating cookies. If you watch me eat cookies, you know, you're not going to feel any delicious at all, because I'm the one who's eating it. All right. And I hope that the sound is okay, and because we are using different sound system today. So are you hearing me okay throughout the lecture?
Yes, I am very clear.
Okay, very good. And if there's no other problems here, question here, let me see you next time. Thank you for being with me today. I feel very welcomed and warmed.
Thank
It's
you so much.
getting. See you later. It's getting into the winter. Stay warm with your jacket. Thank you very much. Oh, by the way, can you hear the music when I played it?
Yes, I do.
Yes.
Yes.
Okay, just checking. Okay, very good. I need to stop recording. I'll see you later, the people from Mars and all the whatever the radio wave is traveling to.